Intro Algebra Lesson 4-2A. Now that you've got a little stronger grasp on how a coordinate plane system works and how we can graph, we can now take that information and apply it to the equations that we've spent a lot of time with, and we can see some relationships with those equations and how they play out in a graph form. So a couple things I want to make sure we're aware of before we get started with the graphs themselves and the equations is the idea that a solution of an equation. Now we've solved equations before and we've come up with values for equations. Now we're going to think about some solutions involving a coordinate and how they relate to those equations themselves. So when we look at an equation and we talk about solving or a solution to it, it's any ordered pair, which again is x and y, that makes the equation true. In other words, it will work if you put it into the equation. Now we're not talking about an equation that has one variable. Now there's going to be two variables. The two variables in the equation will be x and y. So for example, if I were to say, here's a really simple equation. Y equals 2x. Right? That's a pretty easy equation. If you were to make up a number for x like 1, if x equals 1, then y is going to have to equal 2. Because what's 2 times 1? It's 2. So that would be the two values we would get out of that. But things would change if I change the x. If you change x to be a 3, y is not going to be a 2 anymore. 2 times 3 is 6. So this is one coordinate, 1, 2. The coordinate 1, 2 would be considered one solution for this equation. And I just mentioned that if I change this value, it's going to end up changing this value, which means there would be another solution. If you think about it, how many solutions are there actually to this equation? There's an infinite amount of solutions, because every time I change this x, it's going to change that y, and I could change this x to anything. So there are infinite amounts of solutions to equations. I just wrote down one example. All right? When we graph an equation, we're going to try to graph the set of all points, x, y, that are solutions to the equation. Now I just mentioned that in this equation, I wrote down one of the infinite possibilities. There is no way that we are going to graph all of those points. We would be there forever and still not have them all. So what we do is we find a few of them until we start to realize that there's a relationship or a connection between the x and the y values, and we see how that plays out on the graph. Now one way you can do this is you can make what's called an input-output table. So if I make up values for x and y, I'll use the same equation I had up here. Here was one of my x values, a 1. And when I plugged 1 in for x, 2 times 1 makes 2. So y equals 2. And if I plug another number in for x, like 3, now 2 times 3 is equal to 6. So y equals 6. And if I put a negative number in, like negative 4, that's okay. 2 times negative 4 is going to make negative 8. Each of these values that I just created are actually an ordered pair. Now this is a set of solutions to this equation. This is not all the solutions. I just picked 3 different values for x, plugged it in, and saw what it equaled to create some of the other solutions. There are many more. I only wrote 3 of them. But it doesn't require every single one in order to make a graph. But I could take each one of these and put them onto a coordinate plane, and it would create a graph for this equation. And that graph would represent all the possible solutions that would work for it. All right? The last main concept to go over is the fact that what we are going to start dealing with are lines we call linear. And if you look at linear and you kind of erase the AR, what you see is line. So linear, when we say the word linear, we are referencing a straight line. Not scattered, not bent, curved, no V's, a straight line. Straight line produced from the solutions, x, y of the equation. So what I had right here, these values, if I graph these on a coordinate plane, they will actually produce a straight line. So if I were to take them real quick, and grab a piece of graph paper here, and you look at those coordinates, all right, the first coordinate I had was 1, 2. 1, 2 is right there. 3, 6. 3, 6. Then I did negative 4, negative 8. Negative 4, negative 8. And you'll notice that even though they're scattered away from each other, they still produce a straight line. Now, what's interesting is, those are only 3 coordinates. These 3 coordinates right here. But you'll notice there's also a coordinate right there that seems to cross right at a nice intersection on the graph. That coordinate is at the intersection of negative 1, negative 2. And if we test that out on our equation, if you stick negative 1 in for x, 2 times negative 1 is negative 2. So even though I didn't graph that coordinate, I can look at the graph and I can see there's other points. It looks like there's one right here at 2, 4. And sure enough, if you try that out, if you put 2 in for x, what's 2 times 2? It's a y value of 4. So the graph has all the answers. And the fact that there's little arrows here, it means they continue on forever. So even though I only started with 3, the 3 blue dots, I can see that there are many others that are possibilities. There's another one here. There's another one here. You know, there's lots of possibilities as I go through it. All right, our first example. Use the graph to decide whether the point lies on the graph of the line and justify our answer algebraically. So what's going to happen is I'm going to look at the graph and I'm going to decide whether or not the point should be on it or not. So here we have a nice equation. Negative 4x plus 5y equals 15. This is a little more complicated looking than the equation that I was looking at here at y equals 2x. But that's okay. It still has an x and a y value. That's no different. These are 2 possibilities. Now I'm going to graph 5, 7 first. 5, 7. 1, 2, 3, 4, 5. 2, 4, 6, 7. That looks like 5, 7. The other coordinate is negative 5, 7. 1, 2, 3, 4, 5, 2, 4, 6, 7. So that's negative 5, 7. And I think you can tell which one's actually on the graph. It's pretty clear that 5, 7 is actually on the red line, which means that's the solution. That's the one that works. But it wants us to justify it algebraically. All you have to do to justify it algebraically, remember 5 represents the x, 7 represents the y. Plug those values in. So now you have negative 4 times the 5 plus 5 times the 7. And see what it makes. Negative 4 times 5 is negative 20. 5 times 7 is 35. And when you add negative 20 and 35 together, you have 15 more positives. So when I substitute the values of 5, 7 in, I get 15, which is exactly what the equation is supposed to be. If you were to take any dot on this red line, any dot at all, and plug the x and y values in, they would always make 15. If you plug any dot not on the red line, it won't work. Only the ones that are on the red line will actually work. Decide whether the given ordered pair is a solution of the equation. So now this is really what we just got done doing with the algebraic method. We're going to decide whether it actually works. So here is the equation. 2x plus negative 3y equals 23. And here's the coordinate they want to know. Is it a solution? If it's a solution, then I can put those values in for x and y, and it'll make 23. If it's not a solution, I'll plug them in and it won't work. So just remember, this represents x, and that represents y. And so you have everything you have up here, 2 times plus negative 3 times equals. And I'm going to plug 4 in for x and negative 5 in for y. So now we do the math. 2 times 4 is 8. And negative 3 and negative times negative 5 makes a positive 15. And when you add 8 plus 15 together, you get 23, which is exactly what this is supposed to be. Therefore, 4, negative 5 is called a solution. It works. It worked when we plugged the values in. Now, if you mess up and you accidentally stick the negative 5 in for x and the 4 in for y, that's not good. You have to plug the numbers in the correct values, the correct place values. All right, looking at another one like this, remember, this is x, this is y. Everything we have here, you can make the adjustment. I would always suggest a little plus negative there. So now you have 3 times the y value plus -5 times the x value, and we want to see what it equals. And we'll be plugging in a y value of 7. Remember, I don't put x here. I'm going to put the y value in, so 7. And for x, I put in -3. Now, 3 times 7 is 21. And -5 times -3 is positive 15. And when you add positives to positives, you end up with more positives, which is 36. And unfortunately, it's supposed to equal -36. So this is not a solution. Because when we plugged it in, we didn't get what it was supposed to equal. That's all you got to do. That's how you decide whether or not a coordinate is a solution. Can you plug the x and y values in and make it equal the value it says? If you can do that, great. If not, it's not a solution. Find 3 different ordered pairs that are solutions of the equation. Finding 3 different ordered pairs is very similar to what we did right here. These are 3 different ordered pairs. And we made what's called an input-output table. So that's exactly what we're going to do on this. We're going to make an input-output table. What's great about input-output tables is you can choose anything you want. You always start by this, x and y, and you make 3 places that you can put values. Yes, you can still change this to plus negative. I would encourage that. Now you can make up any number you want for x. What I like to say is choose at least one positive, choose a negative, and choose 0. Why not? It's easy to plug in 0. They don't have to be complicated. You don't have to choose 13 or -500 or a billion. You can keep the numbers easy. If you want, you can choose 1, 0, and -1. There's nothing that says you can't choose these values. You've got a positive, you've got a 0, and you've got a negative. There's nothing wrong with that. So plug them in. Plug that 1 in for x. 4 times 1 makes 4, and 4 plus -3 is 1. So we plugged the number in, we did the math, and out popped the y value. That's our input-output table. Now plug 0 in. 4 times 0 is 0. 0 plus -3 is -3. Plug in a -1. 4 times -1 is -4. -4 plus -3 is -7. You have just found 3 different ordered pairs for that equation by simply making an input-output table. All right, let's try it again for this one. Now you have x equals -9. Now this tricks people because they look at it and they go, but there's no y. What do I do when there's no y? That makes it even easier. You still make your input-output table just like we did before. X, y, 1, 2, 3 spots. The only difference is it says very specifically that x is -9. That means that right here, I write -9 for all 3 spots. That's what it is. Now, for the y value, there is no y, which means it doesn't matter what y is. Well, what if y is 7? Cool. X is -9. What if y was 0? Okay, x is -9. You mean it doesn't matter what y is? Nope. Y can be anything at all because x is -9 and that's all this equation really cares about. So you can choose anything you want. 3, 0, -4. Pick any numbers you want for y. All that matters is that x is -9. Well, once again, you've created 3 ordered pairs. All right, one more. Now it just has y. That's okay. It's just like when we had only x. We're still going to make our input-output table. The only difference is this time the y value has to always be -4. So what do you do for the x? Make up anything you want. It doesn't matter what x is. All that matters is y is -4. So you could choose 7, 0, and -5 if you wanted to. But either way you do it, you're still going to get 3 ordered pairs. So again, input-output tables are great because we get to pick any number we want to stick in for one of the variables, and then we do the math, and out pops the other answer. If it's a situation like B and C here where you only have one variable, lock that variable in and make up the other one. You still create 3 coordinate planes, 3 coordinates for your answers.